मैंने सबका कैमरा चालू करा दिया, मेरा ही बंद हो गया।
પ્રશાંત સર જોઈન થયા? સર તમારો અવાજ સંભળાતો નથી પ્રશાંત સર.
નથી થયા સર, હજુ
નથી થયા કેમ કે હમણાં જ
પ્રેઝન્ટરમાં જ એમને સેટ કરવાના છે. પ્રેઝન્ટરમાં
હા, એટલે જ કહું છું કે નીચે આવી ગયા હોય, નીચે લિસ્ટમાં તો જોઈ લેજો.
હા, નીચે નથી આવી,
હજુ લિસ્ટમાં નથી આવ્યા ને? ઓકે,
નથી.
And learning something and implementing some new knowledge in their domain of research and enhance their learning. In the same sequence, today we have a very eminent personality of our system, Government of Gujarat Engineering Colleges. We have respected Professor Joshi sir, Professor Sanjay R. Joshi sir for today's session. He is available. And from the state of Gujarat, participants don't need any introduction of Dr. Joshi sir, but because many participants have joined from other states across the India, almost all states are participating in this program. That's why a brief introduction of Dr. Joshi sir is required. Though 3, 4, 5 minutes introduction is not sufficient for Professor Joshi sir. His contribution is very, that means eminent in our field of electrical engineering. But still we are just doing, that means this we are taking this privilege, and I would like to invite our respected head of department, Professor Vishal Doshi sir, to introduce our today's expert, Professor Dr. Joshi sir. Doshi sir.
Yes, thank you sir. Thank you very much and welcome Joshi sir. I will start my speech now. Good evening everyone. It gives me immense pleasure to introduce an extraordinary personality, a scholar and a leader par excellence, Dr. S.R. Joshi sir, who is with us today to enlighten this session. Sir is currently serving as the principal of Government Engineering College, Surat. He holds the unique distinction of being one of the youngest principals in the realm of technical education, which is a testament to his exemplary achievements and relentless dedication. Let us take a moment to reflect on his impressive journey. Sir began his academic pursuit with B degree from NIT Surat, a place that laid the foundation for his technical brilliance. He went on to earn his master degree from LD College of Engineering, Ahmedabad, strengthening his expertise. He reached the pinnacle of academic excellence by completing his PhD from IIT Bombay, one of the world's most prestigious institutions. What makes Sir career truly remarkable is extraordinary professional journey, and that is here. He has successfully cleared 4 GPSC. I repeat, 4 GPSC exams, a rare feat in itself, qualifying as a lecturer in both diploma and degree education, as an associate professor in degree education, and finally as a principal in a degree education. From starting his career as a lecturer in a diploma institute to leading various engineering colleges across Gujarat as principal, his journey is an inspiring blend of dedication, perseverance, and vision. Sir has brought his expertise and leadership to various parts of Gujarat, having served in Valsad, Surat, Bharuch, Ahmedabad, and Bhuj. This wide-ranging experience embodies both with Vaividyata and Vidvata, making him a truly extraordinary individual. To introduce Dr. S.R. Joshi sir is in essence to introduce the sun itself, a guiding light, a source of warmth and inspiration that fuels the growth and development of everyone around him. Just as the sun brightens the world with its energy, Sir has illuminated the lives of students, educators, and institutions with his vision and wisdom. We are incredibly fortunate to have him with us today, and I am confident that his insight will inspire us all to reach new heights. Let us all welcome Dr. S.R. Joshi sir with a warm round of applause. Thank you, sir. Thank you very much, and welcome once again.
Thank you. Thank you.
So with this note of Professor Doshi sir, just I would like to add one more thing in this. Whenever sir is conducting any practical examinations, after conducting the practical examinations, sir's commitment is like that. He is conducting one session, especially for the students who are not answering well in the practical examinations. I have heard this from the some corner. But that is true, and that is my personal experience also. I was the student of Professor Joshi sir during my MTech at LD Engineering College. Sir's commitment is very much instrumental to shape the career of many students like me, and I am very much thankful to have sir today for this session. And without taking much time, now I would like to hand over the session to you, sir. Now floor is yours, sir. Thank you very much, sir, for joining. Thank you very much.
Welcome, sir. Welcome.
Thank you very much, sir. Thank you.
Am I okay, PK sir? PK sir. Am I
Thank you,
audible
sir.
to all?
Yes, sir.
yes,
You are
sir.
audible.
Yes.
Welcome, sir. See, with this long and very ambitious introduction, I have got a fear that will I be able to deliver good enough or not. Anyway, I will do my best.
Sir, whatever said is exactly truth, है ना? 4 GPSC और जो भी कहा है वो एकदम मैंने कहीं से पढ़ा नहीं है, मैंने जो फील किया है वही
Nothing
कहा
is
है।
atisayokti in this. You are deserving. These words are deserving for you, sir.
Thank you, thank you, thank you. My presentation is visible to all.
No, sir. You just share, please. At the right side, top of the right side, there is one share.
Somehow I am not able to.
No,
See, browse
sir.
my computer. There is, okay.
Everyone can turn off their camera now, please.
Yeah, now
Turn.
you can turn off. Jatin sir, you made compulsorily turn off the camera. Yeah, if you have any query, participants, you can put your question in the chat box. I will put forward to the Professor Joshi sir, and you will get your answer.
Should I select the browse my computer and then upload the file, select the file?
No, sir. Just you just click on the share button at top of the right side.
Okay.
And then share your entire screen. There will be option window sharing. So you share your entire screen.
One minute.
No worry, sir. No worry. We have enough time. Yeah, you close it all and then click on the share button.
Is it visible to all now? Is it visible now?
Yeah. Now your screen is visible and PPT is come.
Yes, sir. Yes.
Okay. So this is the outline of my presentation. First, we will have a brief idea about Indian power system scenario. Then we will discussing few slides on basics of VSC, not from the power electronics point of view, but from the power system point of view. Then we will see the renewable energy interface. Then there are two types of inverters, grid following and grid forming inverters. So that we'll be discussing. Then we'll be looking at the inverter based resources, then inverter control of grid forming and grid following inverters, and then challenges, right? So first of all, I would like to draw the attention of all the participants on this slide. Noticeably, the total installed capacity generation of the generation, it is 462 gigawatt as on 31st December 2024. So this is very recent data. Noticeably, the participation of private sector is 53.7%. That is very huge, and we all can understand that it is a good thing which our government have implemented. The policy is nicely designed and implemented also, and that has resulted into this huge participation of private sector. Also, you can see that the percentage of state sector and central sector is almost equal. So it is not the scenario that states are only having power plants. In different states of India, the central sector power plants are right. So that is also a good thing. If state, all of you know that before the deregulation, if the governments have relied only on the state sector generation capacity, then situation would have been very bad today. But then central sector has also installed many generators, generating plants, and that is the reason why the percentage of both sectors, state and central, is almost same. So that is also a good thing which a power system, Indian power system, has witnessed. This is the scenario of March 2022. All India installed capacity. All values are in megawatt. So the total installed capacity was around 400 gigawatt. 400 gigawatt. The coal has participation of 51%. Renewable energy had 39%. Noticeably, it is 156 gigawatt one of RES. This is the very recent data, December 24, right? The total installed capacity as on 31st December 24 is 462 gigawatt. 2 years back, it was around 400 gigawatt. So I would say around 2.5 years, within 2.5 years, the 62 gigawatt is added. So that is 62,000 megawatts. So huge number. That is also a very huge number. And currently, the coal percentage has reduced from 51 to 46, right? And renewable energy sources is also reduced from 39 to 35.2%. But if you look at that, the total installed capacity has increased. So the installed capacity of RES is also increased. Now here there is a breakup of RES installed capacity. As on December 24, the total installed capacity of RES is 162.5 gigawatt, right? And you can see that the major components are solar and wind, right? So solar is almost 60% and wind is 30%, right? So the solar installed capacity is almost double than that of wind. There are other players, other fuel also, biomass, waste to energy, small hydro, and so on. But this is the larger picture that wind generation is half of the solar generation, right? So solar has picked up. If you see, no, not given. Okay. So this is what the picture. Now, projected installed capacity, all India installed capacity by 31-32 financial year is 900 gigawatt, 900.5 gigawatt, so huge. At the moment, it is 462 gigawatt, here it is mentioned. And within 8 years, from 462 gigawatt to it will be 900 gigawatt. So you can understand the ambitious plan of Indian government. Noticeably, see the current RES penetration is 35.2%, and within the total installed capacity, solar has 40% and wind has 13%. So that makes 53%, right? And here it is only 35.2%. So within 8 years, the penetration of RES will increase from 35.2% to 53%. I'm sure many of you are aware of the fact that Indian government has very good track record of achieving the goal which are set for the RES install capacity. See, energy calculation is also very important, right? Install capacity does not mean that all of the install generators are having plant load factor equal to 100%. That is not the case. So one sample calculation I have given here. Let's say 100 gigawatt install capacity, 24 hours, 365 days. So annual is 876 billion units. Annual energy production for 100 gigawatt, if it is running round the clock for the whole year, then the energy production will be 876 billion unit. So looking to the 31-32 projections, 900 gigawatt is there. So for a 900 gigawatt install capacity, that the energy which will be generated annually is 7,884 billion units. This is a scenario of energy by 2026 and 27, right? So you can see here notably that coal plus lignite, that is based on fossil fuel, is around 59%. So that is very huge. The install capacity is percentage wise of the coal and lignite is of the order of 51%, but here the energy production is 59%. PV is 17% and wind is only 8%. So that makes 25%. So we all know that the energy which could have been generated by PV and wind is, by the, if you look at the install capacity, is very huge, but then due to the poor plant load factor, the total energy generated by this PV and wind annually is quite less. This is the projection for 31-32. See here, by 26-27, total energy generated is 2025 billion unit. See here, for 900 it is 7,884 billion units. Here it is 2,665 billion units. Remember that for the projection for the total all India install capacity in 31-32 is 900 gigawatt. Okay, so for 900 gigawatt, it should have been around 8,000 billion unit, but here it is only 2,600 billion units approximately. So I'm emphasizing here the fact that energy production is lesser as expected if the install capacity is running throughout for the all hours of a given financial year. This is a roadmap how the Indian energy sector is going to transform, right, from March 24 to March 47. So let us focus on solar PV installation. That is, all the figures are in gigawatt. So that is 82 megawatt on March 24, the previous year. By March 30, the projection is install capacity is likely to be 293, means almost 300 gigawatt, from 80 to 300 gigawatt, right? So that is very huge and ambitious plan. By March 47, it will be 1200 gigawatt, only solar I am talking about, right? For the wind, it is 46 megawatt currently as on March 24. From 46, by March 30, it is expected to increase to 100 megawatt. And then March 47, 450 gigawatt. Right. Another interesting fact here is laid down. The same March 24, March 30, March 47. The total generation install capacity by 24 is 453. On December 24, it is 462 gigawatt. By 2030, it is expected to be 777 gigawatt. And by 2047, it is likely to increase like anything, 2075 gigawatt. So these numbers are really eye-catching numbers. as far as the engineering is concerned, lot of engineering projects are likely to come up in this future, maybe by 25 years from now on, roughly. So electrical engineering will have a very good future in the area of solar integration and wind integration. Now see what is going to happen in electricity consumption, right? Currently it is 1620 billion units. It is expected to increase by 1949. So you can see that almost 30% has increased, right? In 6 years, next 6 years, that will increase by 30%. But look at the number 2047, it is 6400 billion units. So that is very remarkable increase. What does it indicate? Indicates that India will have, not only it is due to the increased population, but due to the increased industries, right? Industries are the main components which consume energy, right? So we will have, our economy will grow like anything by 2047, right? Maximum demand met is also very good indicator of any power system. Currently it is 250 gigawatt. It will increase to 334 gigawatt by 2030, and then by 2047 it is 700 gigawatt. So that is the maximum demand met throughout the financial year. This fact is very, very important, and non-fossil fuel-based generation installed capacity, that is 500 gigawatt. Addition, right? Here 300 gigawatt will be added almost by 6 years. So that is very, very important number. Everyone is talking about this number, that the Indian government has planned for 500 gigawatt by 2030. Non-fossil fuel-based generation installed capacity. So this is a number which indicates that what is going to happen within very near future of 6 years, right? So this sector is going to boom like anything, right? Out of it, wind and solar installed capacity at the moment is 138 gigawatt, but by 2030 it will be 393 gigawatt. So this number also indicates that something big is going to, I would say something huge is going to occur in the RE, renewable energy scenario in India. So this number are really eye-catching. So this is the important fact. That's why I have made a separate slide for this, that by 2030 non-fossil generation installed capacity is to be 500 gigawatt. And most importantly, net zero emission by 2070. That is the projection by Indian government. VRE, it is nothing but variable renewable energy. Here in this case, the last row, that is of VRE. So VRE installed capacity will be 393 gigawatt by 2030. Why it is said variable? Because it is intermittent and difficult to integrate into the power grid, right? You may have connected it, but then the integration is very, very difficult. There are many issues which we'll be discussing later on. VRE includes wind and solar power which generate electricity based on environmental conditions. Wind and solar both. A present VRA capacity is 145 gigawatt, December 24. The share of VRE in 500 gigawatt goal is 392 gigawatt, 393 gigawatt. Okay, now let us discuss something technical. General structure of RES integration. So what is it? Energy supply system, be it wind, solar or battery even, right? Then power electronic interfaces are there, and this together this both component together, the term given to this both component together is inverter based resource, IBR. We will be discussing on IBR later on later slides, right? So this IBR is connected to grid, right? So that is the general structure of RES integration. Let us look at a typical PV array. It starts from basic PV cell, right? One PV cell typically the power rating is 465 watt peak, 3.175 volts rating, current and voltage rating, 1.467 ampere. Now here you can see that there are 6 columns, right, and 12 rows, right? So this makes a one module of PV module, right? So together all these cells, 72 cells, right? The total power rating, peak power rating is 335 watts. Voltage rating is 38.10 volts and 8.80 ampere, right? So from this 8.80 ampere, we can infer that the 6 columns are connected in parallel, right? See the current rating here, 1.4, right? And from the series, 12. So 12 3 are 36, right? So this 12 are connected in series, right? So this is how the arrangement in PV module is made. Now let us turn our focus on PV array. So this PV array has the peak power rating of 1 megawatt, right? The voltage rating is 1.18 kV and current rating is 0.85 kiloampere, means 850 ampere, right? So one array is 96 strings in parallel. Oh, this is the string, right? And in one string, 31 modules are in series, right? So this is what a typical arrangement of a typical PV array. Now this is a schematic diagram of a typical RE power plant, right? There will be a PV array. Between PV array and VSC, voltage source converter, there will be DC to DC converter if it is required, right? And then this together, the whole system is connected to the grid. This is even more detailed schematic diagram where you have got DC load between DC to DC converter and DC to AC converter. This is your VSC. You can have battery also if there is a provision. And then this is a bus, right? That bus is known as point of common coupling, PCC, right? Through this bus, the connection is made to the grid. Now at this bus, you may have connections of auxiliary power supply like diesel generator, wind, biomass, and so on. And you can have AC load as well, right? This is very basic 3-phase 2-level VSC. The devices are IGBT. The VSC converts DC into AC. So 3-phase terminals are shown at the output terminals. This is a 3-phase 2-level VSC with square wave switching, right? Now this is some technical aspect. So on the left hand side, are you all able to see my cursor when I move it?
Yes, sir.
Okay. So cursor, let me change. Okay, is it now visible?
Yes, light is visible, sir.
Oh, no, I'm saying cursor.
No. Cursor is also visible, sir.
Okay.
When you are moving your, that means a pointed cursor, it is visible from our side.
Yes. Thank you. So this VSC is connected to grid, right? So the switching is square wave switching, as I have given in title. So this is what you will have voltage, right? A phase voltage will be stepped voltage. So there are 3 levels, right? Most important fact here, which I have, the reason why I have kept this in my presentation, magnitude of fundamental component is fixed. You cannot vary the magnitude of fundamental component which is available at the output terminal of VSC by having square wave switching. So the VLL line to line voltage is root C by pi into VDC. Because VDC is fixed, your VLL line to line voltage is also fixed, right? Another is important, very, very important aspect here with the square wave switching is from the waveform, it appears that this stepped voltage waveform will have lower order harmonics which are dominant, and that will require big filter in size and obviously space and cost and everything, right? But at the same time, with square wave switching, by shifting the instant of this square wave switching, you can control phase and frequency. So that flexibility is here. But with PWM switching, magnitude of fundamental component is controllable. So that is the very, very important tool which we have when you want to integrate RE into the grid, right? So that is very, very desirable, right? Another important aspect with PWM, you can suppress the lower order harmonics, right? The magnitude can be reduced as well as some harmonic, lower order harmonics can be eliminated together at all, right? So that results into smaller filter. So that is another important advantage having PWM switching. So phase and frequency, as it was controllable with the square wave switching, here also it is controllable. So these 3 points are very, very important for connection of RE to the grid, because we need to control this VSC for various disturbances, voltage stability, frequency control, and so on. There are many challenges, right? So for all these challenges, these aspects are very, very important. That's why I have kept this in my slide. So here it is PWM inverter. Filter is there in between the transformer and the inverter. There is a VSC hour. So this is your AC side. Transformer is there. This is the line. This is the inductor line, right? And then it is connected to infinite bus, or let us say it is a grid. In this representation, where inverter is connected to grid, harmonics and losses are neglected. Okay. So as we have seen that this M, see what is this M? I have mentioned here magnitude of fundamental components controllable. Means M is controllable, right? VDC is constant. Here the grid voltage has phase angle phi, right? Okay, so this EC is the voltage fundamental component, voltage generated by VSC, fundamental component of voltage of VSC. Okay, so that is alpha. So that also I have shown here that the phase is controllable, right? So this alpha is controllable. The alpha is the phase of EC. So M and alpha are independently controllable. See, this is also important point, that both are controllable independently. So that is very, very much desirable. So now the steady state equations, remember these are the steady state equations, not dynamic. Please note this. Inverter connected to grid, right? So how the power flow occurs from the VSC or the RE to the grid. Your E angle phi is the voltage of the grid. So this is a phasor, right? So your active power expression, active power supplied by RE source to the grid is very well-known formula, ECE by XT. XT is the net reactance between the two voltages of grid and voltage of VSC, and sine alpha, right? Because alpha is the phase angle difference between the two voltages, right? The voltage of EC is phi plus alpha, whereas here that of grid is phi. So the difference is alpha. So that's why it is sine alpha only. This is important. the expression of Q is very, very important. The reactive power exchange from the RE source to the grid is extremely important, right? It is not that RE is for supplying of energy and hence active power is only important. No, it is not so. The expression of the exchange of reactive power with the grid is also very important. You can operate your VSC in such a way that in some certain conditions it absorb reactive power or supply reactive power, right? So both way it is possible. So the expression of Q here is minus E square by xt plus ECE by xt into cos alpha. So these are the very well known formula. Those who are working in power system field, they are very aware of these formulas. Power balance, this is also very important. VSC is here, DC side, AC side. The incidence power is VDC, IDC. So this is the equation which balances DC power. On the right hand side of the equation, it is AC power, right? So under balance steady state condition, I repeat, steady state conditions, the average of product of VDC and IDC is root 3 VLL, RMS, IRMS and cosine beta. That is the power factor angle, right? On both the side of this equation, there is active power, right? Now, if VDC is almost constant, the variation is not really very high. It may have some harmonic, but then magnitude of harmonics in the voltage is very low. So you can consider VDC as constant. So the product of VDC and average IDC is root 3 VLL, RMS, IRMS, cos phi, right? So average of IDC only dependent on active power and not affected by reactive power. From this equation, we can conclude this, right? I repeat, the current drawn by VSC, which is IDC, the average of this IDC depends only on the active power, right? So what does it mean? That the reactive power supplied by the VSC, amount of reactive power supplied by VSC, or the amount of reactive power which is drawn by VSC, absorbed by VSC, does not affect IDC at all. I hope this point is clear to you all. This is very important to understand, right? STATCOM and BESS, battery energy storage system, right? If this switch is open, this is only STATCOM, right? So this is your capacitor on DC side of your VSC with some voltage, right? Remember that with this, because there is only capacitor, the STATCOM cannot supply any active power, right? So on the AC side of VSC, it cannot supply any AC power. So that's why PAC is equal to 0. QAC can be controlled, right? Likewise, I have discussed in my previous slide, right? Now, capacitor on the DC side is adequate as average IDC is 0. Average IDC is 0 because what I have concluded here, that average of IDC depends only on active power, whereas here no active power is supplied by the STATCOM, right? So a smaller size of capacitor is also enough at the DC side terminals of this VSC. If I close the switch, where here I have battery and DC to DC converter and then VSC, our VSC. So in that case, PAC and QAC, you can supply to the grid active power as well as reactive power, right? And the important fact is both can be controlled independently if we have got battery, right? PAC can be negative. Now PAC can be negative, which means when the battery is being charged, it draws active power from the grid, right? So that's why PAC will be negative. This is the RE interface. Okay. This RE source is supplying active and reactive power to the grid. EC is already mentioned here. But as far as control of this RE is concerned, it requires some information of the phase angle of the grid voltage, right? And we already have seen that the controllable parameter of VSC is M and alpha, right? So at power electronic level, the firing level, right, we can control M and alpha, right? So this M and alpha are controllable by varying the firing of the devices, right? Okay. So this P and Q can be controlled by controlling M and alpha, that is by controlling the firing. Important point here is frequency is logged to the grid frequency by PLL, right? So phase lock loop is very, very important and it has to be there. This is a typical operational mode of RE interfaces, right? This is what typically happens in our grid at different plants of RE. So this is a schematic diagram of PV inverter. PV array is there. It supplies DC voltage, DC power, then it converts from DC to AC, and then it is connected to AC grid. Here we introduce the term grid following PV inverter, right? Grid following. Why I'm saying it is grid following? You can observe here PLL, right? The input to the PLL is VABC, right? So that is the grid voltage. If you can see here that VABC is here, right? So that is supplied to PLL. That gives information regarding this phi, right, to PWM, right? Okay. So there are two possible modes. One is MPPT and other is other controller, higher level controller, right? So to this controller, the command given is power command. So this power command is also supplied to this controller by even higher level control. This is the lowest level of control. Second level of control, that is the primary, secondary, and tertiary, which is not shown here. So here there are series and parallel connected array, which we have seen like this. This one, right? Okay. This DC voltage is not regulated, remember, because here there is a PV array, right? So it depends on the solar insolation. So this VDC can be varied, right? Okay. Then we have got VSC, and then through transformer, appropriate voltage step up, it is connected to grid, right? Here PW output of the PW is the firing pulses that is given to the VSC. Okay. VDC is also given to PWM. The phase angle from PLL and frequency both are given to PWM, right? And this is the input is the desirable M and alpha. So that signals of M and alpha is generated by the current regulator, right? So this is what the typical control of grid following PV inverter. Why we say it is grid following? Because the frequency of this output of VSC is logged with the help of PLL, right? So that is why it is said that this inverter is grid following inverter, right? Okay. So either of these two signals are there. So these are the current commands. So this is the set point of in-phase component of the current, which is responsible for the active power. This IR star is the set point of the quadrature component of the current, right? So these both are given to the current regulator, which generates M and alpha using IABC and VABC. So these are the grid current and grid voltage, right? this particular section of this whole control scheme, if you look at, so it is very, very fast acting, right? As I have told you, this is the primary control loop, right? Shaded portion is the primary control loop. It is relatively fast acting. This is your secondary control loop. So it is slower than this particular shaded controller. And then the tertiary is even further slower. Okay. Now let us turn our attention to the grid interaction. What happens when the inverter is supplying power to the grid, right? So using appropriate transformer, this is your bus, right? Then there is a system. This is the equivalent system reactance. It may be a transmission line, right? And then it is connected to the grid or say infinite bus. Here there is a VSC voltage. This is a bus voltage, right? Some important fact I have noted here. If the system reactance is low, this X is low, I would say the whole RE installation is connected to a strong system. If this system reactance is low, in that case, bus voltage will be relatively insensitive to VSC voltage and P and Q injection. If you vary P and Q, if this X is low and if you vary P and Q, the bus voltage is likely to be insensitive. So the variation in voltage is lesser if X is low. Lesser in which case? When this P and Q, first you vary P, then you vary Q, and you can vary both also simultaneously. But for all those variations, the change in bus voltage will be lesser if this X is low, and vice versa, right? If the system reactance is high, then bus voltage change will be higher for the same P and Q injection. Okay. For the controller, a weak system is vulnerable to adverse interactions, as I have explained earlier, right? So this schematic diagram shows about the signal output and input, right? So PLL takes on bus voltage, then it gives a bus voltage also given to the controller. Here I am saying this bus voltage is given to this controller also. PLL output is given to controller as well as VSC firing, right? So this is the controller generates voltage and current M and alpha, right? Power system, this current is IABC, right? And this is my VABC, right? The VSC voltage, then there will be transformer, transmission system and all. So that is embedded within this power system block. So we were discussing grid following PV inverter. Now another type of inverter, grid forming inverter, right? That was grid following. This is grid forming inverter. So this weak grid, right? Dotted portion shows a weak grid, or it is a passive load here connected, not an active load. Active load do not supply energy. It is drawing power only, right? Passive load. So grid forming VSC, this is grid forming VSC, does not use a typical fast acting PLL because this is not grid following. PLL is used by grid following inverter only. So this PLL is locked to the grid voltage using grid voltage. So that's why we say this VSC is grid following. Here, if it is a weak system or there is no weak system, this weak system is not there, only passive load is there, then there is no voltage, right? Grid voltage is not available, right? So it is not using a typical fast acting PLL. Frequency or the phase of VSC voltage is determined in a different manner than grid following inverter, right? If only one grid forming VSC is connected to a passive load, then voltage magnitude and frequency can be fixed internally by GFM, grid forming inverter. I got only half an hour. Giri
Hello?
sir?
Yes, sir.
Oh.
You can carry on, sir. No worry.
Okay. Oh, I will try my level best.
But it's going very interesting, sir. You please carry on.
Well, it is up to participants.
Yeah, sir. Actually, I can see the interest of the participants. They are just keeping continue listening.
Oh, is it?
We can see the expressions as well. Some participants are expressing. Just you can see the expressions.
Well, I am not able to see. I am just focusing on presentation. But in grid forming inverter, even if the frequency is not fixed, it is varying. The variation is of course low, but then it is not constant. The voltage magnitude, frequency and phase of grid forming VSC, they are constant for longer duration than grid following VSC following disturbance. So here there is a comparison for a given disturbance, right? So same kind of disturbance is given to grid forming inverter and grid following inverter. In that case, these quantities, voltage magnitude, frequency and phase, are constant for longer duration, right, compared to that of GFL. This grid forming inverters require some power margin, right, or storage to be available to achieve this, which I have mentioned in point number 3. Which is an ideal GFM inverter? It is fixed voltage magnitude. If a single GFM grid forming VSC is connected to passive load, then frequency can be fixed. But power frequency droop is required for stable operation with other GFMs or synchronous machines. So this, I'm sure the faculty members are knowing about droop, PF droop, right? That is must for proper sharing of the active power among the different GFM and between GFM and synchronous machine. So that drop is very, very important. IBR. What is IBR? So it is grid connected facility which has a power electronic interface between the AC grid and the source of electricity. It includes modern wind turbines, be it by type 3 or type 4 wind turbine, solar photovoltaic, battery energy storage system, HVDC, FACTS, in case of FACTS, STATCOM and SVR. They are connected to grid at transmission and sub-transmission level. See, this point is important, that IBR are not connected to distribution level. They are connected to transmission and sub-transmission level. Distributed energy resources are the one which are connected to grid at distribution level, right? So this DER and IBR, they are different. See, this grid forming, grid following, IBR, all these terms are they have become very, very important because of increasing penetration of wind and solar across the globe, right? And the size has increased like anything of a given power plant, right? So unlike previously, the research was focused on DERs, right? Now it has shifted to IBR. So those who wants to do PhD or research, then this is a very good area because the penetration or the install capacity is going to increase phenomenally, right? So huge installation are going to occur. That's why I have given around 10 slides on the Indian power scenario. By definition, I will skip the definition, right? The RES share in overall installation is increasing. The behavior of IBR is much different than that of synchronous generator. The behavior of IBR is primarily determined by the control strategy employed by the VSC. The challenge faced is due to the unique technology. See, there are many manufacturers of different IBRs. So the VSC, filter and so on, right? Even the PLL and PWN and all, right? There are many manufacturers. They all have different unique technology, right? So that is the reason why at a given power plant, let's say there are two different supplier manufacturer of different which are using different technology, then it becomes very difficult, right, to integrate power of both these IBR. For simplicity example, I'm giving up to manufacturer only, so that integration of energy to the grid becomes very difficult, right? And that is why there is a need of standards of all these control techniques, which are the key component. And I am shortening, actually, I'm sorry to shorten. Energy source, inverter, step-up transformer, collector system, all are the key component of IBR. Plant substation, plant controller and protection, tie line and point of interconnection, right? Magnitude and frequency of voltage can be controlled. That already point I have discussed. Very fast and flexible ramping is available. See, with the solar, I'm sure all of you are knowing that in the morning, the ramping up of solar generation is very high. In the evening, the ramping down of solar is very high, right? It is the inverted bell shaped characteristic is such. So this fast ramping is very important, right? So this IBR, whichever IBR is employed, it must have this fast ramping feature. Fast frequency control is also very important. That is, it is the advantage of IBR over synchronous generator. In case of synchronous generator, fast frequency control is not possible because of the huge inertia. In this case, it is possible. Grid is being transformed rapidly by more and more IBRs. So this is the case everywhere, all countries. Proper integration of group of IBR is very crucial. We will come back if time permits to these slides. This is a typical layout of RE plant, right? You can see that wind farm, then here it is the power converter station. Here 600 volts to 33 kV transformers are there, wind and PV array. So this is 33 kV bus, right? So at this bus, filter bank is connected. Here reactive power compensation is provided here. This is very, very important. Time is not permitting, so we cannot discuss this. Then there is step-up transformer from 33 to 220 kV. So this is a substation, right? So this bus and this transformer, they might be at the same location. Then 220 kV generator bus. This grid is very far from this 220 kV bus. So you require HV cable or overhead line, right? This PPC is nothing but the power plant controller, right? So from here, see, this grid voltage is given to the PPC, and this reference voltage, power, active power, reactive power, and frequency are given here to PPC, right? And output of the PPC signals are given to this reactive power compensation, VSC connected to the PV array, and the VSC of wind farm, right? So this 220 kV bus is known as point of interconnection. So this whole system is a plant of RE. Challenges: variation in generation, both wind and insolation. We all know that is changing. Unpredictability creates problem in generation scheduling. This is very important aspect which is faced by the power system operators at the load dispatch center, right? For example, if your wind penetration is very high, that create a problem. You all must be knowing that scheduling is dispatch. Power generation is dispatched to every generator in 96 blocks in India, right? 15-minute block, right? So 24 hour, 96 blocks. So every block power dispatch is given, right? Similarly, it is given to wind also. Now, if penetration is very huge of wind and suddenly wind falls, right? So generations drops. So that is very problematic, right? So that is very big challenge for the integration of wind power plants into the grid. To handle these challenges, energy storage system can be employed. I have given here example of dropping of the wind speed. So similarly, in opposition to this, wind speed can increase also. solar insolation can increase also, right? So in that case, energy can be stored in the battery, or when it is required, and the battery can supply at transmission level, right? Means this level. I am talking about this level. Variation in line flows is required due to above mentioned factors, right? So in a conventional system, the possible ways to control power flows is very limited. You cannot modulate the power flow through AC lines with good flexibility. But then for the desired power flow control, HVDC and FACTS can be used. Other challenges are scheduling and dispatch, transient voltage stability, frequency stability, load generation balance at various time scale. Now here, various time scale means the 15-minute block, hourly block, a day block, week block, month block, something like this. Restoration from dark. So if there is blackout, so how to restore the total system? So in this case, IBR can be very, very useful, right? Because they generate power using solar and wind. So they are very, very helpful, right? If there is no wind and solar in the system, then restoration from the dark, from the blackout can take many, many hours, like 2 or 3 days. But with this kind of higher penetration of wind and solar, it can happen in within 12 to 15 hours. The another challenge is protection of power system to which IBS are connected. Then this ride-through capability might be discussed by other experts. So that is after disturbance or the fault is very, very important, right? It can be ride-through, low voltage ride-through, high voltage ride-through. These are the different ride-through which are discussed, and research is also being carried out by many researchers. So this is also another challenge. Modeling of the whole system with IBRs is another challenge. It is still in the research phase, right? So it is desirable to have model of new IBRs, right, which are accurate, right? And the challenge here is that there are different manufacturers, different technology. So that's why the modeling is become difficult. Another challenge is to control the voltage and frequency. This also might be discussed by other experts. Converters make it possible to control both with high speed. That is the advantage of power electronic converters. The control of voltage and frequency is required at steady state as well as during disturbance also. This is important fact. So might be somebody might think that the control of frequency and voltage is required during disturbance only, but no, it is not so. At steady state also, the control is very, very much important. Okay, so here for the better operation of power system with IBRs, it is important to have a strong and safe system. Already I have made a point here in one slide. So if a major portion of system is grid following IBRs, right? It is not grid forming, grid following. It impacts the stability of the system. In short, a strong AC system is beneficial for operation of grid following inverters, right? If the penetration of grid forming inverters is very huge, then it is not a good situation, right? Few more challenges: steady state over voltage, right? Voltage fluctuation due to intermittency in generation. It is applicable to wind as well as solar both. Interaction with distribution equipment, right? So voltage regulators, step changes and capacitor banks, etc. So these are all controllable, right? So they interact with the distribution equipment. Reverse power flow. This is very, very big challenge and problem which has occurred due to the penetration of high level of penetration of REs, right? Conventionally, the lines were having power flow only in one direction, right? But with the penetration of RE and connection, the power flow has become reverse also. So that is creating problem for scheduling, the forecasting as well as protection also, right? Voltage unbalance is another challenge. Temporary over voltage is another technical issue. Then because these all are power electronic converters, harmonic injection is also has become a problem, because the level of harmonic injection is also very huge. Then variability of power output is also a challenge. Protection and control, short circuit current contributions. So fault level, so that study is to be carried out by the utility companies and the power plant operators, sorry, power system operators. So they have to carry out short circuit current contributions from these IBRs, right? So the model, correct model for short circuit studies is required. Another area for the research. Unintentional islanding, that happens, the events are occurring of this nature. Then line losses, change in real power flow in feeders. These are the challenges. 15 minutes. Let me try now. See, reactive power is injected at a bus. If it is injected, it causes increase in voltage. Whereas if you absorb, it drops the voltage at that particular bus. But the most important factor here, which I want to bring into your notice, is the degree of this change in voltage depends on the equivalent Thevenin's reactance or short circuit reactance. So I am referring this reactance, right? Okay. And other factor is X by R ratio. So I will discuss now both this effect of this both factors. See, at a receiving bus where the voltage is V, right? So the line reactance is X. So the grid is supplying current I to the inductor connected at the V. So no load is connected to focus on the effect of X. Okay. So that compensation is called as inductive compensation. Now see the voltage phasor here, because it is inductor, current is 90-degree lagging, and the voltage drop in this, that is Ji of the line, that is Jix. So that will be in phase with V, right? Because of only inductor is connected here, right? So summation of this V and this drop becomes E, and because the current is 90-degree lagging, right, to the E also, right? The resultant current is lagging to E because the X is inductive only and the load connected or the compensation current is also the inductive only. That's why the current I lags 90-degree from E also, right? So here you can see that the reactive power is being absorbed, drawn by the load, right? Inductive compensation. So what is the result of it? V is less than E. V is less than E. From the phasor diagram, it is very clear, right? It is opposite in case of capacitor. This is the phasor diagram of V. Again, as before, I is leading the V by 90-degree, and obviously this Jix is the drop. So in case of inductive, the angle of Jix is 0. In case of capacitor, it will be 180, obviously, right? So E is less than V, right? Or V is greater than E. So what is here proved, that for the capacitor compensation, voltage rises, then it is more than E, right? For inductive, the voltage at this bus is less than E, right? So in a weak system, that is high X, right, greater changes in voltage occur for same reactive power injection or absorption. So if this X is high, so what will happen, that the phasor length of this drop will increase, right? And that V minus E or E minus V will increase, right, for high X. Lesser change in voltage occurs for the same reactive power injection absorption for a strong system or low X. I will explain using phasor diagram. Now system with low X by R or the high R, such as of cables, right? Note that a group of IBS are connected through cables only at RES side. So the aggregation of energy from IBR to, let's say, 33 kV bus. So from this point to this point, from this point to this point, normally it is done through cable. Real power control. Here you can see that X by I have added R here. So X by R ratio has increased. Let us assume that R is higher. Now, for simplicity, the reactive power supplied by this is as made to 0, set to 0. Not necessarily. Here there is an inverter, right? Your line. So here this inverter may supply or absorb reactive power. But for simplicity, here the exchange of reactive power is banned and Q is set to 0. So this PV system is supplying only active power, right? So this current I is in phase with V. See here, this because it is supplying, right? If it is drawing, then V and I will be in phase. If the V phasor has 0 angle, I will have 0 angle. But here it is supplying. So I is having 180 degree phase compared to V. V has the phase of 0, right? So this JIX and JIR, and this becomes resultant E, right? So X by R ratio here is 1 and here is 3. So you can very easily understand that the voltage drop or E minus V is more in this case, second case, right? So higher R or the low X by R results in greater change in voltage with real power exchange. So that is the impact of it. What are the issues? Standards of BESS, DERs, grid forming capability of inverter, protection settings. This is required, right? Communication standards, load modeling standards for EVs, electrolyzers, data centers, etc. They are all required. See, there is one interesting case, right? The problem is of forecasting, right? See, this is one event of solar eclipse, 20th June of 2020, right? And on the next day, 21st June of 2020. So the blue line is the all India solar generation from 9 o'clock to 3 o'clock afternoon, right? So this blue indicates that power generated by solar of all India, right? Next day on 21st June, there was solar eclipse, which has started around 10 o'clock and it was up to almost 1:30 p.m., right? So you can see the drop in the solar generation, right? The maximum fall in the active power generation due to the solar only was 11 gigawatt, 11.1 gigawatt. So 11,160 megawatt. You can see, right? Now this one cannot predict that how much drop will occur in megawatt generation, active power generation. So this creates problem in scheduling. Remember, this time duration is also very short, from 10 a.m. to 1:30. So almost 3 hours, right? The thermal power plants are not suitable for ramping up and ramping down this much huge generation, right? So this is a problem typical problem of RE generation. So see here, this is the blue line indicates the forecasting of solar and wind, right? On 24th July 2024, right? On the x-axis, horizontal axis, these are the blocks from 1 to 96, right? So blockwise, these points are plotted here. Now this dotted in violet color, right, is the error, right? And error is calculated actual minus forecasted, right? So you can see that this error is negative whole day. All 96 blocks, error is negative. Error negative means the actual generation was less than the forecasted. So see, you can see the problem faced by the power system operators, right? The maximum error was 7,479 megawatts, right? Question is how to fill the gap of this much magnitude, right? So this is a huge problem for the power system operators. Shall we go for okay? Another issue is, see, if you can see here, the circle is light colored and the color it becomes darkens as fault level in MVA is increasing. First it is 10,000 MVA, 20,000 MVA, 30,000 MVA, 40,000 MVA, 50,000 MVA. Now here you can see in the region of Rajasthan that there are more points which is light color, lightest color, right? So they expanded here. Fault table is of your 10,000, 20,000 and so on only, right? Which indicates that this system is weak. And you see the pool generation, it is 1,000 megawatt, 3,000 megawatt, 2,500 megawatt and so on, right? So the problem which we have discussed here becomes predominant. I hope you understand by what I'm saying. This X is weak, it is high, right? And huge amount of power is being pulled, right? So the this voltage becomes very sensitive to the towards the change in active power injection and reactive power injection in this remote area of Rajasthan because of the low fault level. This should have been higher, fault level should have been higher. This is uncertainty in inter-regional corridor flows. See, the northern import. You can see the northern import is positive also and negative also, right? But magnitude is of the order of 4,000 to 6,000 megawatts. Here it is almost 5,000 megawatt. Import is, import positive means NR region is drawing power. Negative means NR region supplying power, right? Now see here in this figure, again the horizontal axis represents the 96 blocks, right? This both or all four plots so that bidirectional flows is occurring. And because of RE penetration and which is increasing day by day, year by year, this is going to happen. Bidirectional flow will be there in transmission lines. Okay, here also in the southern region also the same case is observed, right? See, in Rajasthan on 11th August 22, the one event has occurred which has 6,000 megawatt was dropped in the solar power plant due to face-to-face fault in 220 kV line. So this is creating havoc, right, for the power system operators. Very difficult to handle such situation. Giri sir?
Yes, sir.
There are not many slides here. I would like to stop here so that.
Yes, sir. Almost time is up, sir. And yes. Thank you very much, sir, for your wonderful session delivery. Now, I hope so. A few questions has been there in the chat box, and we will take very few questions. The reason is I can understand the busy schedule of Dr. Professor Joshi, sir. He has so many academic as well as administrative assignments. That's why we cannot take much time. This was enough, what the sir has given from his busy schedule. Now, there is one question in the chat box. Respected sir, due to integration of inverter-based resources into system, micro coordination of relays occur. how to resolve this issue. I think so. This question is somewhat not based on the content delivery, but this is related to power system question, and basically he is asking about when RES is integrated into the grid, what are the challenges occurs in relays coordination. Hello.
Please.
Sir,
So
his question is related to our
I,
REF.
I am not expert on power system protection, so I'm sorry for that.
Yeah. Actually, I was knowing this because Mr. Ravindra Kishan Rao Mankar, this question can be answered better by the experts of the protection system. Because Professor Joshi sir is the expert in power system, renewable energy integration, as well as load flow studies, short circuit studies, and
Dynamics.
dynamics, load dynamics, and all power system dynamics, voltage stability. So these things are related to this delivery, and we are sorry to not properly answering you, but you can understand limitations as well. If any other query, please you can ask. Okay, I hope so, sir, because your delivery was your session was very informative, and it was crystal clear, because I have learned a lot of things, and I hope so similar from other participants as well. And whatever you have discussed from statistics of the renewable energy generation, solar, wind, share, power scenario, and then various challenges, you have given certain directions as well. How to conduct research when someone is integrating renewable energy power into the conventional grid, what will be the various challenges. You have discussed in length, and you have given certain directions in the further research. So this session overall, it was very informative for power system students as well as for power electronics also. I am basically from power electronics, but I can understand whatever you have discussed here related to grid following converters, grid forming as well. So overall, I hope so. It was very informative and useful to all the participants, and definitely they are going to learn something from this session, and they will use the contents whatever provided by you in their future work and research, and definitely they will keep update their students as well after learning from here. So it was very wonderful session, sir, and we are fortunate enough to be with you here for 1.5 hours. And it's our pleasure to invite you, sir, and very much thankful on behalf of Government Engineering College Bharuch. Though we have all worked under your guidance in Government Engineering College Bharuch also, and these things were initiated from your level in 2022, basically, and then it continued to be in process. And I am very much thankful to you on behalf of entire organizing team, including our principal, Professor Dr. P.P. Lodha sir, respected head of department, Professor V.Y. Doshi sir, and all our teammates. Sir, our good wishes with you. You continue to do good work for our system, sir, and our all the best wishes with you. May God bless you with good health and everything, sir. Thank you very much, sir, for joining.
Thank you. How
Namaskar.
many
Good night, sir.
participants from Gujarat?
There are 29 actually. Registered participants were quite more. Nearly 51 people have registered from our system. But we have been given the permission of only 30 participants, and out of 30, 29 are continuously attending the sessions.
Okay, so that's really good. I hope someone is getting motivation from this presentation and doing research in case of the integration of RE into the grid.
Yeah, sir. It is very burning topic, and nowadays it is very much required, and there is a lot of scope Where there are many literatures and very nice papers are available in this area. And whatever you have guided us, it is going to be very useful to all the participants. And from our system also, few people are doing PhD participants. We can see there are so many participants are continuing in their PhD studies. So they can use the fundamental concepts, whatever you have discussed here in their research, and definitely it is going to be beneficial to all of them.
Thank you.
Thank you very much, sir. Thank you. Thank you for joining, sir. Thank you.
To listen me with patience. In the end, I had to speed up little bit, and sorry for that because content was such, right? So thank you all to listen me with patience, and thank you.
Thank you, sir. Good night. Good night.
Good night. Good night to all.
You. Thank you very much,
Yes.
sir. Thank you.
Oh, Sasa.
Participants. PK sir, yes.
Yes, sir. Thank you very much.
Okay. Welcome.
Yeah.
Thank you, sir.
Thank
Divyesh.
Divesh Parmar.
Oh, Divyesh, thank you, bhai.
Welcome. Thank you so much, sir.
Now, dear participants, I think so the time has come to that means to say that means our Joshi sir to say goodbye, and we will start our next session with Professor Dr. Sabharaj Arya sir within few minutes. Just we can see here whether he has joined or not. Divesh sir, make the Sabharaj Arya sir as a presenter.
Yes, sir. 1 minute.
Okay, so I will leave by. Thank you.
Yes, sir. Thank you very much, sir. Thank you. Thanks. It's our pleasure, sir.
Welcome, welcome.
Okay, sir.
Always welcome.
Thank you, sir. Thank you. हाँ सर ज्वाइन करिए हाँ हाँ आराम से करिए हेलो
Yes, sir.
Sir has joined.
No, sir.
एक बार चेक कर लो.
हाँ, कर.
अभी नहीं ज्वाइन किया. एक मिनट, कुछ इश्यू हो गया. हाँ सर. हाँ, वेब ऐप पे चले जाइए. हाँ, वेब ऐप पे अपना ये यूजर आईडी पासवर्ड जो माइक्रोसॉफ्ट ऑफिस का, गूगल में मत करिएगा. ये तो वहाँ यूजर आईडी पासवर्ड मांगेगा. तो पासवर्ड एक बार बदलवाएगा वो. अच्छा, एक मिनट. नहीं, आ जाएगा. वो थोड़ा सा हैरान करता है. Sir has joined us. Attendees, make him presenter. Yes.
Okay.
So, yeah. Now, our next eminent expert, Professor Dr. Safar Ajaria sir has joined us for the second session of third day. And we are going to start the session very soon with very brief introduction of Dr. Safar Ajaria sir. Just please wait. Actually, sir is a professor. Currently, sir is working as a professor in electrical engineering department, Sardar Vallabhbhai National Institute of Technology, Surat. Sir is a member of IEEE since 2012 and senior member and promoted as a senior member in 2015. He received the Bachelor of Electrical Engineering in electrical engineering from Government Engineering College, Jabalpur in 2002. That means 2002. And MTech from MNNIT, Allahabad in 2004. And sir has received his PhD under the Quality Improvement Scheme from IIT Delhi in 2014. He is working in the electrical engineering department of SVNIT since 2006, and he became associate professor in 2019 and became professor in 2023 at SVNIT Surat. His area of interest includes power quality, power electronics, power filter design, design of DC-DC converters, and distributed power generation. And there are few more accolades in sir's credit. He is the recipient of 2 national awards, namely INAE Young Engineer Award from the Indian National Academy of Engineering and POSOCO Power System Award from the Power Grid Corporation of India in 2014 for his outstanding research work. He also received the Amit Garg Memorial Research Award 2014 from IIT Delhi for high impact publication in quality journals, mostly in transactions, IEEE transactions and IET transactions during the session 13-14. In the year 2023, he has received Tata Rao Prize from Institution of Engineers, India for his research paper. He has published more than 150 research papers in journals, and most of the research papers are having great quality, published in mostly in IEEE transactions. And Sir is also included in Thomson Reuters and Stanford University ranking, in 2% scientist ranking, since last 3 years. He is also serves an associate editor for the IET Renewable Power Generation, that is the highly rated journal of United Kingdom. So this was very brief introduction about Sir, and I was fortunate enough to work under Sir's guidance. I was the PhD student of Dr. Arya Sir since 16 to 19, and I was gained a lot of exposure under the Sir's guidance. So we are fortunate today also to have great time with Sir. Sir has given his valuable time to us for this session. So directly I would like to invite Sir for his session. Now, Sir, the session is yours.
Thank you for introduction. Now we will start lectures in the area of DCC converter first. Then we will go towards custom power devices, and then more application custom DCC converters. Why are you na?
Yes, sir. You are visible, audible, both. Hello. Yes, sir. If internet problem is there, then you can turn off your video. Or audio is very clear.
Maybe video. Are you okay now?
Yes, fine, sir.
Oh.
Please continue.
So that is clear. Now we are going to discuss about the design and control of high gain DC converter and interface in solar system. Means point is, in this whole lecture we have designed one high gain converter with solar system, and their output we are going to provide the one load, but one means isolated load frequency. Here we will see some part of introduction. Then we will see the voltage boost techniques, high step up topology, their simulations, and then PV battery integrated standalone system for DC grid, their simulation and hardware. We will see. Then you can see in the introduction, we see the system, how system we have developed. This is the one type of example only. Solar system, then DCC converter. Here we want to step up the voltage up to maybe 2 times, 3 times, 4 times, 5 times. Here we have done up to 4.2, 4 to 5 times. We have step up the voltage, 50 volt to 200, maybe nearby that. Then one more point is there. In this application, maybe we want to equipment all the DC voltage at particular bus only. Then from that bus we are going to supply to us as per requirement. DC loads, DC to AC load, then grid we can connect, DC to AC converter and fan we can run. But depend upon the application, we are going to put different types of loading. From input side, we have solar PV, maybe fuel cell, maybe battery, maybe ultra capacitor. Whatever energy storage system are there, so in that place we want to store the power from solar system, and that power we are going to step up. That voltage we are going to step up based on the grid DC bus requirement. This is our point. Means we have many DC sources. I mean that many DC sources means some may be going to charge, or some may be going to provide the power daytime, or maybe depend upon their conditions. Suppose solar we have, solar is going to provide the power daytime, then we can charge the battery, one thing. I mean, fuel cell we can use, then fuel cell also we are going to provide the input to DC converter, and that DC converter quality is high step up thing. We all the means maybe one we cannot, maybe more than one we cannot connect. This is converter. That converter is going to provide the required level of bus voltage, and that bus voltage we want to convert in AC value. Means here we cannot say only we have 4 sources. Many sources, many possibilities are there. Hello?
हाँ सर.
हाँ.
हेलो.
हेलो.
हाँ स्लाइड चेंज नहीं हो रहा है.
नहीं अभी हुआ होगा ना, अभी मैं चेंज नहीं किया.
अच्छा, इसको फुल शेयर कर दीजिए सर, फुल में.
हाँ फुल में है.
फुल में नहीं दिख रहा है एक्चुअली.
तो
ये स्लाइड शो में चले जाइए, स्लाइड शो में कर दीजिए.
हाँ स्लाइड शो ही रखा ना, अभी आ रहा है.
एक मिनट, उसको क्लिक करिए स्लाइड शो वाले को.
हाँ स्लाइड शो, हाँ क्लिक किया. आ रहा होगा.
स्लाइड्स तो आ रही हैं, बट उसके साथ वो सब ऊपर का पूरा दिख रहा है ना, इसलिए चलेगा. एनीवे, आप केवल स्लाइड्स चेंज नहीं हो रही थी, इसलिए मैंने इंटरप्ट किया. ओके सर.
तो अभी देखिए, now we can see this one. Now we are able to see that voltage boost technique. Hello.
हाँ सर, वोल्टेज बूस्ट टेक्निक वाली स्लाइड आ रही है.
हाँ, now voltage boost technique, in that we have a multi-stage or multi-level converter. In that we have cascaded, interleave and multi-level converter. You can see maybe switch capacitor and or charge line. In that type of thing also be there. Then voltage multiplier means voltage, we have a voltage multiplier cell or voltage multiplier rectifier we can design. Next one, switch inductor or voltage lift converter means here we have designed this converter, switch inductor or voltage lift converter. Or maybe also we can design a system based on the magnetic coupling, transformer and coupling inductor. Means in this converter, now many converters are there, many possibilities are there, and all those converters they are going to cost not more than 3,000, 4,000. Means one hardware we can make it, then maybe not more than 3,000, 4,000. Means in that case you can see cost of inductor and capacitor, that is common for all the converter. Only we are going to change the small device also common only we are going to change the diode and maybe small capacitor, maybe small resistance only. Small inductor capacitor. Based on that one we have developed the many converter topology. Or maybe in terms of low power application, 2 watt, 3 watt, 4 watt, 5 watt, that also possibility are there. Means we can develop the technology for any level. Means maximum we have very low power level only. So see, one of the new converter you can see. This is the one of the new converter, and that converter we have developed. This is the based on the many diode that connections. You see the converter, how converter is there. This is the one type of new converter only. Basically, after development of new converter, that we want to see the states across the devices, switch across the devices, across the diode, inductor, capacitor. That states we want to measure. We want to view the states, and we want to get maximum voltage at output side. This is our basic point. So here we have a new two switch isolated DCC converter, isolated high step up DCC converter with reduced voltage states across the switch. So see, suppose input voltage we have given, then we have a two switch, S1 and S2. Okay, then we have how many the diode 1, 2, 3, 4, and 5 diode is there. Then based on diode, we are going to base the boosting phenomena. Then you can see the inductor is there, 2 inductors. Then primary side transformer, then they are supporting LM also is there. Then one more inductor is there. So in that case, first we need to understand how circuit is going to operate in switch on and switch off mode. Means to enter in this area, first we need to knowledge of the buck boost and that specific or maybe cut converter, whatever they have given in maybe normal power electronics book. After understanding that point, means after understanding that their constant means that CCM and DCM mode, then we can go towards some higher converter. Those converter, each converter has a benefit. Due to that benefit, we want to develop new thing. We want to maybe apply, maybe after some application, maybe you are going to change your connection of diode, inductor, and capacitor. Then we are able to develop a new converter. That new converter useful for certain application. You can see. So basically, here point is there. he have developed one new converter that is based on the diode, and that diode converter is going to boost the voltage from input to output almost 4 times. And their controller also, you can see in each case we need to compare reference voltage and output voltage, PI controller. Then that output of that one you can compare with the one carrier wave. Carrier wave in case of DC converter, we have to take a carrier wave in sawtooth form only. Based on that one, you can decide the switching frequency. Then you have one PWM. Then depend on the number of switch, you can get the more pulses. Maybe based on the hello.
Sir, sorry to interrupt you, sir. Slides are not moving actually.
No, till now I am in the same slide only. The same slide I am telling you. Slide number 3 only. Hello?
But sir, actually we are not able to see the changes.
Changes means I have not changed. Nah? Then how you can see? When I will change, then it will change. Nah? Till now I am in the same slide only. Slide number 3 only. I am just telling. Okay. Then point is there. Whatever means you can see that in all the DC converter, possibility of change in control is very less only. In this case, basic control is we want to sense DC link voltage, output of voltage. With how much we want to put, how much we want to maintain, that you want to put there. Then error you can find out. Then regulate the error component. After regulate the error component and how we can tune the KPK, that is one more theory there. Then means by tuning the value of KPKI, you are going to maintain the output of this loop is minimum constant DC. Means output of PI is minimum constant DC are based on that DC value. Means whatever DC you have got, that DC you can compare with the one sawtooth wave. Based on the sawtooth wave, you can decide the switching frequency. This is one story. Again, point is there. Here, where we can work, which place we can work. That is main point. One point is you can develop converter. Develop converter also easy, not a typical, but cost is also less. We can develop a small power level, 10 watt, 20 watt, 50 watt, 5 watt, any value. That's our requirement. Suppose we want to put 10 volt to 50 volt, that also possibility are there. 50 to 200 also possibility are there. Depend upon our budget, we can develop new converter. That is point. This is the one new thing. Second thing here, how we can tune the PI control. That is also many points are there. So in that is the second point for new contribution. Third point is also you can decide the switching technique. What type of technique you are going to use, how you are going to switch on the converter. That also point are there. That means here 3 points are there. Based on that one, we can develop new thing. Okay. After development of converter, suppose we have developed the converter. Now we want to see how converter is going to operate. Means simply we cannot put some means switch and that diode and inductor capacitor, and then we want after connection we want to make one switch on mode and switch off mode. In switch on mode, energy going to store, and switch off mode, energy going to release. This is called phenomena only. When switch is on, so see the how when switch is on, see the mode number 1, see the arrow mark. Based on that one, you are going to observe power in the output side. Output side means after transformer, power is going to transfer. Here you are going to see what the role of transformer. Transformer is going to provide the isolation, galvanic isolation, as well as the after means transformer secondary side. Now you are going to observe the high frequency AC, and that we want to rectify. That is the point. Means transformer input is a DC. That one is going to convert in from a high frequency AC, high frequency to high frequency AC. We want to convert. Then after that, after conversion of that voltage in high frequency form, then we want to rectify. So this transformer is going to work as a one. This means isolation only, high frequency to high frequency. Okay. Second case, first case inductor is charged. Second case switch is off. Now you can see inductor number L and L2. They are going to release the energy, or that release energy going towards primary side of transformer, and they are going to transfer to a secondary side. Means point is there. We need to read converter operation first one. Mean how energy going to store, how energy going to release. That is point. Then you can see. After that you can see here we have given input voltage how much? We have given almost 48, 49 volt. We have given input voltage in simulation form, and output also you can see near to 200. Then after that you can see the input current and output current. If input current is near to 30, output current is going to reduce. So because they want to, means system is going to maintain the power balance. So you can see here input voltage less, output voltage high, but input current is in percentage form, or that is somewhat higher value, but output is near to 0.8 and maybe 1 ampere. You can see the gate pulse. Now see the gate pass based on that your duty cycle requirement, how much you want to boost. Based on that one, you can based on your requirement, you can say the duty cycle here. Now next stage. Again, one more converter we have taken. This is the second converter. In this converter, a new single switch isolated DC converter. Here we are going to use only one single switch. Where is the single switch? This is the S1. S1. How many diode? D1, D2, D3, D4, D5, D6. 6 diode we have used. Still, we have not given any name here. This is the switch inductor and voltage lift technique based on that. So means we want to boost the voltage and base our system based on the switch inductor only. Inductor we are going to switch on. Inductor means due to switch inductor going to charge. That you can see. Controller you can say similar to previous control. Nothing more change here is there. Just you can sense reference and actual voltage PI. Then compare with load current. In this case, one point is there. We need to compare with load current. Okay, that load current and your PI output you can compare. Then we have a X2. That X2 based on the value of X2, we want to get the gas signal for connected switch. Here we have only one single switch only. This is the system based on the single switch. So mode 1 you can see. This is see the how system is going to operate. So you can supply voltage. We have put solar. Solar means solar means maybe 10 volt you can take, 20 volt you can take, 50 volt you can take. Depend upon your budget, how you are going to develop the setup. Maybe 2 watt, 5 watt, 10 watt, that also possibility are there. People are not telling you can make 200 watt, 500 watt. Okay. Now you can see here we have 2 loops are there. First loop is you can see this. You can see here loop supply solar. After solar ID2, then L2, then this S1, then you can see one side this capacitor and diode, these things are there. You can see this. Second loop inside of that is a yellow color loop. You can see there are output side. If second case, if switch is off. Now, if switch is off means supply solar panel, then inductor diode, then one loop is there. One more loop is going towards that D5, D6, C1, C01, C02. Second loop you can see blue color. Third loop also you can see C1 not, C2, C01 and C02, then output side. Means here basically we have called first we are going to charge, second we are going to discharge the system. That is point. The second case we don't have any switch. In this case you can see we have given 50 volt near to 48 or 49 volt. Then we are going to see output near to 200. Input current and output current you can see. So input current you can see many ripple are there. Many means 4 to 6 that one is going to vary. Then current is going to become maybe 1 ampere, 2 ampere depend upon your conditions requirement. Duty cycle near to 50% we have taken here. Okay, means basically we want to boost the voltage. A voltage boosting we want to do based on our requirement. And if voltage is going to boost, current is going to decrease. Then you can see one more single switch ultra high gain DCC converter with voltage lift technique. Again single switch based on the ultra high gain. Again more gain we want to improve. More gain we want to get here. So see here how this circuit look like. Supply voltage L1, C1, C2, C3, 3 capacitor, diode you can see D1, D2, D3, D4, D5. 5 diodes are there. So how many switch? Only one switch. There should be want to switch on based on that this whatever control logic we have seen. Okay. Here control logic generally not possibility not there to change the control logic. Less possibility are there only. Because 1 or 2 switch we are going to observe and that change is very less. Means doing change is very less chances. But another size chances are there. We want to analyze the circuit. We want to develop their stability. We are able to develop their transfer function. We are able to develop their stability transfer function. They are plotting. That is a possibility are there in this case. Now you can switch it on. See the how circuit is going to work. Supply voltage L1. Then switch. Then one loop. Okay, red color. Then you can see second loop. You can see blue color. C3, D4, C02. Then this loop, blue color loop you can see. Third loop also we can observe D2, C1 and C2. Green color loop you can see. One more loop you can have done in the output side. Here you can, in first loop you can see from source inductor going to charge through the switch. So then we are telling this is the single switch ultra high gain. And then after that this power is going to transfer towards C3 side, C2 side. And then again in load side power is going to transfer from C02. From that capacitor power is going to transfer towards C01 and C02. That loop is going to work and we have an output voltage V0. Okay, see how power is going to transfer in switch on mode. First inductor charge, then after that some power is going to transfer in blue loop, then the green loop, then after that you can see value of C00, the capacitor, that capacitor power is going to transfer C01 is same branch only. Again we have one closed loop system only, then power is going to transfer towards load side. This is the switch on stage. Second case you can see. In second case, switch is off. We don't have any switch now. Supply voltage, inductor, then power is going to transfer towards C2, D3, C02, then this complete loop you can see. Red, green, then below that blue is there. Some part of power also will go towards C3, C5 and load side. Then again one blue loop you can see. C3, D5, R0, then ground side you can see V in this one loop. Okay. Then this is the loop number 1, loop number 2, loop number 3, loop number 4. We have 4 loops. 1, 2, 3, 4. Okay. So finally, our when switch is off, inductor is going to supply the power to us R0 or maybe finally as a V0. Okay. Means here basically point is there. In this case, cost of the project, cost of the implementation is so easy. So easy means we have to we should have inductors. A 5-6 inductor you can buy, you can purchase some capacitor, you can purchase, put some diode. Easily we can develop maybe 50,000, maybe more less than 50,000. Many converter we can develop. Whatever inductor we have used, that inductor is going to use for another converter also. Inductor capacitor common only, diode also common. Just only we want to connect here and there. We can take inductor based on a single value only. We can take inductor based on the multi-tapping. You can see whatever inductor we have purchased here, 0 to 10 millihenry, and 1, 2, 3, 4, 5, 6 we have put the tapping. That is a high frequency inductor only, small size only. You can take 5-6 converter, you can develop the converters. Okay. The next point is see how we can find the transfer function. We can plot Bode plot, Nyquist plot, root locus, that possibility also there. Then you can make the state space that analysis. Based on that, you can find about AX plus B. You can do AX plus B. You can do based on the A matrix, B matrix, C matrix, D matrix. You can find out the required stability phenomena. Then you can plot. So means this one is also going to add the one more component on your search work. Just paper writing available in the other place. Now in this case, you see the third converter, same voltage we have given, near to 48, 49 volt we have given. We want to measure 200 volt. Hello.
हाँ सर, ये स्लाइड का अभी कौन सा नंबर आप चला? स्लाइड रोल नहीं हो रही है यहाँ पर।
11 नंबर है अभी, 11 नंबर का
नहीं है, 4 पे ही है यहाँ तो।
क्यों हो रही है सर?
स्लाइड्स मुझे लग रहा है कुछ इशू हो रहा है, स्लाइड रोल नहीं हो रही है।
यहाँ तो ठीक है सब, यहाँ तो नेटवर्क भी ठीक है।
हाँ अभी रिजल्ट्स आया, लेकिन इसके पहले वो 4 नंबर पे ही स्लाइड अटका हुआ था।
अभी कहाँ पर है?
एक बार ऐसा है तो फिर से शेयर करिए, रीशेयर कर दीजिए।
अभी कहाँ पर है?
अभी आपका ये स्लाइड नंबर 12 है, स्लाइड नंबर 12 दिख रहा है।
11
एक्चुअली 11 ऊपर है उसके, अभी नहीं आया 11, अटक गई है स्लाइड एक्चुअली। एक काम करिए ना, इसको फिर से एक बार रीशेयर कर दीजिए। अभी भी नहीं जा रहा है। हाँ अभी आया 10 नंबर। इंटरनेट का भी इशू हो सकता है।
हाँ सर, वो टाइम लैग की वजह से हो रहा है थोड़ा।
हाँ थोड़ा इंटरनेट का इशू हो सकता है, फिर से शेयर कर देंगे तो हो जाएगा मेरे ख्याल से।
आप बताओ।
अभी तो आप शेयर करिए। हाँ अभी आ गया, 10 नंबर आ रहा है।
यहाँ ट्रांसफर फंक्शन वाली।
हाँ ट्रांसफर फंक्शन वाला आ रहा है।
हाँ, नाउ you can see here based on the state space analysis means
अभी आप
we are
11 नंबर पे, एक बार 11 नंबर पे जाइए तो यहाँ देखते हैं 11 नंबर आया कि नहीं आया। 11
आ
नंबर
गया।
पे जाइए।
आ गया नंबर, आ गया मैं।
नहीं आया, अभी भी 10 पे ही है।
क्यों नहीं आ रहा वहाँ पे? यहाँ तो जैसे चेंज हो रहा सब।
लेकिन इधर क्या इशू हो रहा है ये समझ में नहीं आ रहा है।
अभी 10 नंबर, 10 11 नंबर गया।
अभी 10 नंबर पे चल रहा है। हाँ दिवेश, तुम्हारे एंड पे क्या दिख रहा है?
सर वो ट्रांसफर फंक्शन वाला ही है दिख रहा है अभी।
अब उसके बाद
हाँ।
सिग्नेचर रिजल्ट एंड क्लोज लूप ऑपरेशन।
वो स्लाइड
नहीं
साइड
आया।
में दिख रहा है, लेकिन वो अभी आपने उस पे क्लिक किया है। 11 नंबर क्लिक करिए जरा।
कर दिया, मैं क्लिक कर दिया।
हाँ लेकिन वो रोल नहीं हो रहा है आपका इधर।
नहीं 11 10 ही आ रहा है, 10।
10 नंबर ही आ रहा है।
अभी ये 14 15 पर आ गया ये।
एक काम कर सकते हैं, ऐसा है तो हमारे एंड से स्लाइड रोल कराएं, या तो फिर
हाँ ठीक है।
आप स्लाइड ऐसा है तो हमें शेयर कर दीजिए, तो हम अपने एंड से इधर से रोल। दिवेश थोड़ा तुम स्लाइड रोल करो उधर से।
आर्या सर,
हाँ
सर आप कंट्रोल F5 करिए, वो शेयर हो जाएगा पूरा स्लाइड फुल
कंट्रोल
स्क्रीन में। F5।
F5।
F5। हाँ हेलो सर, सर इसमें से निकल गया क्या लगता है?
वो फिर से ज्वाइन हो रहा है सर।
हाँ सर, ज्वाइन कर लीजिए टीम को। हाँ बस बस यही ज्वाइन कर लीजिए। हाँ ज्वाइन करिए। हाँ
है।
हाँ आ गए आ गए।
हाँ, इसके बाद शेयर।
शेयर करिए।
शेयर क्या करूँ? शेयर विंडो। हाँ
हाँ शेयर करिए, स्क्रीन शेयर करिए।
ठीक हुआ।
एंटायर स्क्रीन शेयर नहीं हुआ अभी आपका। आया आया। हाँ अब आप कंट्रोल F5 कर दीजिए।
F5 कर लूंगा फिर वो सब चला जाएगा।
ऐसा है, बाहर
वो
निकल जाते
फंक्शन का
हैं।
भी की
हाँ।
होगा सर आपके अंदर।
अब चालू ठीक है। अभी
नीचे विंडो है ना सर, वो लास्ट वाला, वहां पर क्लिक कर दीजिए तो फुल स्क्रीन आ जाए। वो एक्चुअली फंक्शन भी दबाना होता है, तो वो
कहाँ
आपके
पर?
आप नीचे जो बॉटम में वो विंडो टाइप का है ना, फर्स्ट वन जूम के बाजू में, वहां क्लिक कर दीजिए तो फुल स्क्रीन आ जाएगा।
फुल स्क्रीन तो है, यहाँ से फुल स्क्रीन दिया हुआ है।
नहीं फुल स्क्रीन में फिर ये दूसरी स्लाइड्स नहीं दिखनी चाहिए ना, बाकी स्लाइड्स भी दिख रही हैं आपकी।
तो दूसरी कौन सी दिख रही है?
ये एक साइड आपका, ये सारी स्लाइड्स खुली हैं, फिर वो जिस स्लाइड को सेलेक्ट करते हैं वो स्लाइड आती है, तो ये फुल स्क्रीन में नहीं आता। फुल स्क्रीन में केवल एक ही स्लाइड आएगा।
तो फुल स्क्रीन है, ये फुल स्क्रीन किया मैंने।
हाँ ये नहीं नहीं, अभी भी नहीं। एक मिनट बताते हैं। ये नीचे जो है, हाँ, इस पे स्लाइड शो कर दीजिए, स्लाइड शो।
आ गया अभी?
कुछ प्रॉब्लम है, मुझे लग रहा है नेटवर्क का ही कोई इशू
नहीं
है।
आ रहा अभी, नहीं आ रहा है?
आ तो रहा है, लेकिन जो आप सेलेक्ट कर रहे हैं स्लाइड, वो रोल नहीं हो रही है बराबर।
अभी
नहीं, आपने 10 नंबर का सेलेक्ट किया है, अभी 11 नंबर पे जाइए।
11 पर आया।
हाँ, लेकिन यहाँ नहीं आता है 11।
कहाँ से आएगा ये? या फिर मैं ऐसे करूँ, एक ऑप्शन और है। अब यही वाला ऑप्शन।
आर्या सर,
हाँ,
आपके जो विंडो है उसके ऊपर WPS टैब में लिखा हुआ है, सेकंड नंबर पे होम के बाजू में WPS PDF।
ऊपर लेफ्ट हैंड साइड, ऊपर लेफ्ट हैंड
ऊपर
साइड।
लेफ्ट हैंड साइड पर होम के बाद
WPS PDF।
हाँ
हाँ,
हाँ,
उसके ऊपर एक सिंबल है, देखिए वो फुल स्क्रीन
ये?
करेगा। उसके ऊपर
सिंबल
एक
पे
सिंबल
जाइए,
है।
सिंबल पे, ऊपर सिंबल है।
क्लिक कर दिया। अब
तो आपकी स्क्रीन पे आ रहा है फुल स्क्रीन?
हाँ, मैं आज फुल स्क्रीन आ रहा है इधर। उधर आ रहा है क्या?
यहाँ
इधर तो
नहीं
नहीं
आया
आ
है
रहा।
सर।
अभी कुछ करते हैं, रुकिए। PDF में कन्वर्ट करके कर दीजिए ना, PDF शेयर करिए इसको। स्लाइड्स PPT छोड़ दीजिए, PDF में कर लीजिए। सेव एज PDF कर दीजिए स्लाइड को, PPT को, और वो शेयर कर दीजिए। सेव एज PDF वो पहले ओपन करिए, PPT। हाँ, हाँ, कोई भी एक फोल्डर में डाल दीजिए।
अब
या एक काम करिए तो
हाँ,
दिवेश परमार शेयर कर देंगे आपका
हाँ,
स्लाइड उधर से।
मैं जस्ट ओपन कर रहा हूँ इधर। अब देखो वाला,
नहीं आ रहा है।
देखो अभी कर रहे हैं। अब शेयर के बाद स्क्रीन विंडो। अब आ रहा है?
आया तो सही, हाँ, अभी आया।
सर।
नाउ
अभी
इट्स
आया।
फाइन। हाँ, यस यस यस।
नहीं तो फुल स्क्रीन कहाँ से करेंगे अभी?
बस अब फुल स्क्रीन ही है, अब इसको रोल करते जाइए आप।
फुल
केवल
नहीं,
वो
आप मेरे पास फुल नहीं है ना, आप है।
आ गया ना।
नहीं, यहाँ फुल नहीं आ रहा है।
ओके सर, यहाँ हमारे यहाँ आ रहा है।
इधर फुल आ रहा है, अब आप केवल उसको रोल करते जाइए, स्लाइड वाला चलता रहेगा।
फुल कहाँ से आता है? फुल कहाँ से आएगा?
Ctrl+I।
कंट्रोल
+I।
कंट्रोल। ठीक है, आ रहा है।
हाँ यार, इधर आ रहा है अब। ये दिस इज फाइन सर, इसको ही
ठीक है।
कंटिन्यू करिए आप,
ठीक
इधर
है।
रोल होने लगा है।
ठीक है,
हाँ, ओके सर, फाइन।
नाउ वी कैन सी।
थोड़ा सा पीछे रिवाइज कर दीजिएगा, वो जो नहीं रोल हुआ था ना।
हाँ,
कनेक्ट। हाँ,
now we can see in back side we have this three converter topology. First one is voltage boost techniques. There we have taken switch inductor or voltage lift technique we have converter we have taken. In that case, first two switch topology we have taken. Second, one single switch topology we have taken. Third is one single switch ultra high gain DC converter topology we have taken. Now we can see after analysis of the converter, we need to develop their mathematical analysis based on the state space, and we want to find a transfer function. Other transfer function, based on a transfer function, we need to plot their 0-4 plot, and we need to do the stability. In this case also you can see what ultra high gain DC converter is there. In that case 50 volt we have given. Output is near to 200. Level of current is you can see near to 4 to 5 ampere and smooth current. See the output current near to 1 ampere. Due to power balancing, that current and voltage level is going to change. See the duty cycle here, maybe 30 to 40, 30 to near to 35% duty cycle we have put here. And see the level of input current and output, both are smooth near about. Compared to backside previous converter, here you can see many ripple component we have observed on DC input side of the converter. So this is the advantage. Now we want to see. Now you can also see the how our result is going to change. Our converter output is going to change with the dynamics. In for dynamics, we have put one 2 ohm resistance, 200 ohm resistance, a second one 300 ohm resistance. Input voltage, output voltage we have taken input 48 volt, output is 200 volt. Now voice is coming, na? Hello? Hello?
Sir. Yes, perfectly
sir.
going, sir.
Now you can see input voltage, how much we have given? 48. Output near to 200. Then input current 5 ampere, output 1 ampere. See the switch current, switch voltage, switch current, capacitor voltage VC1, VC2, VC3, VC01, VC02. Those we have observed. Okay. Then after that, we have put the dynamic, we have changed the load now, 200, 300 ohm, and see the how all the parameters going to vary. This is our requirement. We want to change the load from one position to second position, a second to again first position. So all these cases you can see the different whatever component we have connected across that voltage, across that current we need to see, across that voltage and as well the current flowing through that component we have observed. Also you can see first case all the capacitor voltage we have taken, second case all the diode voltage we have taken, D1, D2, D3, D4, D5. So see all the converter near to 50 volt they have maintained. Switch can to 20 ampere and input can near to 4 ampere. So moving 5 times or 4 to 5 times we have higher current across the switch. Now we want to see the comparison of all the whatever 3 converter we have done. In this case, all 3 converter means converter number 1 is going to provide isolation, 2 and 3 they are not going to provide any isolation. That point is there. Nature of input can discontinuous, then continuous with refill and with less refill. That also we have observed. Output voltage control by duty cycle and transformation test ratio by varying duty cycle. By varying duty cycle we can control. Second and third by duty cycle control we have controlling the output voltage. Component require 2 switch in first converter. Till now converter we have to converter 1, converter 2, converter 3. And that name we have given. Converter 2 switch converter, 5 diodes, 2 inductor, 2 capacitor. This much component we need to design this one. Converter 2 for design of converter 2 switch, 1 single switch, 7 diode, 2 inductor, 2 capacitor, 1 transformer. Okay. Third one, single switch, 7 diode, 2 inductor, and 2 capacitor. The load filter also, first case only 1 filter, 1 capacitor, second case 2 capacitor you can see. To see the diagrams, this is the third one, no isolation, 2 capacitor. Second one, 2 capacitor, no isolations. First one, isolation with this one. So means point is there. Here we don't require transformer maybe. This is a mistake maybe they have written in this point. This transformer you can put with first one. 2 switch, 5 diode, 2 inductor, 2 capacitor, 1 transformer in first converter. From second converter you can remove the converter. You remove the transformer. That point. Okay. So see, this is the component. Based on that one we have developed the system. Again you can see requires Sonoma circuit, First case we need, second case no, third case need a single lossless inductor as a solver circuit. Protection against the input side current, so yes. Second case no and no, third one. What is the output voltage? In first case you are going to see output voltage equal to capacitor voltage only. But in second case, output voltage equal to capacitor voltage 1 and capacitor voltage 2. The capacitor voltage divided in two parts, 1 and 2. Third case also, capacitor V naught equal to VC naught 1 and VC naught 2. Switch voltage stress. See the voltage, see the stress across the switch. So see Vs1 3 V in 1 plus D divided 1 minus D. In case of second switch, 2 V in D divided by 1 minus D. In converter 2, you can see Vs equal to V in into 1 plus D divided by 1 minus D. Third case, Vs equal to V in 1 divided by 1 minus D. So based on that one, we can calculate the switch voltage stress. Now next one, how much gain we can observe? Voltage gain. This is our requirement. How much voltage we can boost? So N into V in 1 plus D divided by 1 minus D in case of first converter. In case of second converter, N is not there. 1 plus 2D divided by 1 minus D. Third case, 3 into V in divided by 1 minus D. So see the formula. Based on that, we can calculate. See the output voltage in converter 1, converter 2, converter 3. In case of converter 1, sharply voltage going to change from near to duty cycle 0.75 to 0.85. Second case, somewhat sluggish. Third case again somewhat higher. See the how output is going to change with the help of with duty cycle that we have plotted. In first converter, you can see within some advantage there based on that connections. Now you can see now we have developed this one PV and battery integrated standalone DC grid. So we have taken that PV system, meaning 59 volt that PV module we have taken. Then one high gain converter we have designed, and we have maintained that 380 volt DC link, a DC capacitor. So one DC load is there, just you can connect and you can view that load. That load is going to take that voltage. Next case, now second case we have designed one bidirectional DCC converter. That DC converter going to take the power from the DC bus and going to charge the battery. This is one of phenomena. Second phenomena is there from battery also we can take power. Okay, these 2 points are there. So this type of system we have developed. In this case, again we can see how converter going to operate. The first purpose converter we have used. Then we have used that input as a solar. Then output is V naught. Then 380 volt. Then after that, after DC bus, we want to charge the battery. Then we have used one purpose bidirectional DCC converter. Purpose converter we have taken, by that one we have charged the battery. Okay, this is one of the complete system you can see. Solar, high gain converter, then one DC bus. The DC bus you have connected to DC load. Then from DC bus also we want to charge the battery. So we have connected one bidirectional DC converter. Any converter you can connect. Maybe here we have put simply one buck push converter. Any other converter also can be high gain converter. Maybe any other special technique, special output based converter you also can connect based on the battery requirement. Then here again more topology we can change. To see here how that bidirectional converter going to that switch on. To see here reference voltage, output voltage, reference current and battery current. Based on that one you can find out the set value of the I battery set. Okay. Or then the I battery set you can use as input to the second loop. You have a battery current. Then PI controller. Then you can set the duty cycle. Okay. Again point is there. Then find out the value of the second loop. You can see duty cycle and carrier signal. YB you can see. You can see X2 as a output. The X2 as a output you can take and carrier signal we are going to take. Then we are going to compare. Then we have a D2P. D2P means that second one. And again NOT signal D2N, first one. Then also we can see DPV. DPV means and DPV. Then a 70% based on the 70 maybe SOC, we need to select that duty cycle for PV and duty cycle for second PV. So this is one of the control logic for this one. For how we can control that high gain converter, the PV voltage, PV current you can take, then zero order hold we can put, then you can use, here we have one PSO technique to tune the value of KPI here. Whatever PV voltage, PV current are coming, base means then we have one MPPT here based on that you can say that you can say PSO, that error we have got, and then we have get the PWM generation or DCC converter. Okay, so we need to see some more possibility in control also. Now you can see in simulation how all the data we have put here. Open circuit voltage V0 36 volt, source current 7.79, MPPT 29, current is 7.8. Solar PV array we have taken two number of that series connected PV string. Number of para connected 3. Open circuit was 72. Source circuit current 23. Total power near to 1200 volt. MPP voltage MPPT 59 volt. Current is 21 ampere. These are data. Okay, for solar PV. Then similarly we have designed the value of high gain DCC converter parameters. Then you can see the other parameter we have given here. Input power, input voltage, output current, input output resistance, frequency 50 because we have taken duty cycle 53%, switch rating you can see, inductor capacitance voltage stage you can see 59, C1 C2 have almost 126 and 190 nearby. Now you can see inductor, refill inductor 4% we have taken, the alone we have designed, then capacitor C1 C refill 1% we have taken, C1 we have designed 107.09, C2 is again 107, C3 is 53, C01 is 57, C02 is 82. Then see that by in simulation we have set 6.44 gain. Voltage gain is near to 6.44 times. Same thing also we can see in bidirectional DC converter design parameters. The input voltage you can see here. Input equal to battery voltage equal to PV minus bus voltage. Then bus voltage you can see, battery voltage we can see, current also we can see, frequency 50 kHz, duty ratio is 53 for buck mode and that 47 for boost mode. Inductor L 13.1, capacitor C 100 microfarad, CV for battery case 13.2, voltage gain is 6.44. Means when we are going to design the converter, then we need to set this value, that is for simulation purpose. Now we can see. Now we have seen the system response. By changing the radiation, see the voltage, PV current, inductor, then temperature you can see, S1 current, S1 voltage, then PV power. Similar you can see DC side also 380 volt we have put the DC that bus voltage 1.9 ampere current, bus minus battery is near to this value, VC1 is near to 130, VC2 is near to 125 127, VC3 that value, VC01 is 125, VC2 is near to 170 255 nearby that. Then see that now we have changed the load also. By changing the load, you can see all those parameters. So here you can see the SOC, how SOC is going to change. Now battery current also going to reduce now. Here you can see that you can see SOC also going to change. See the value of voltage across all these switches. And now we want to analyze that. Our means that switches are more safe compared to some hard switch based system. Now you can see the bus voltage 380, error you can see, PI output, battery reference current, error 2, PI output 2, DP2 and D2N, means 2 D2P and D2N. Those duty cycle, how much duty cycle we can put, that we cannot observe, no, that is very less time only. So that due to that the continuous they are showing. Okay, meaning of this one is when we are going to plot the result, so first we need to see their means input and output relation. That is our requirement. Then after that we can input output means input current, input voltage, output current, output voltage. Then we can see from where power is coming. Their parameter we need to see. After that, we can see all the system parameters, whatever thing we have connected, input side and output side. Then in one window, you can plot maximum 7 to 8 curve only, not more than that. Maximum 10 you can plot, not more than that. So due to that one, we have taken so 3, 4 that window you can see. After that, you can see now we have developed. You can see the converter. This is a small converter, na? Small means you can see purpose high gain converter, hardware setup. You can see this inductor we have taken, inductor 1, 2, that we have taken from market only. And then after that, on PCB we have put this component. Small PCB, general purpose PCB there, na? In that breadboard you can say, not general purpose PCB. This is a simple breadboard only. So here we have connected component. Then we have got the result. Nothing new theory, nothing new point is there. Just only you can design the system, then you can connect. Then we need to design the gate pass also. We need to design the control logic. So for that one, you can use your processor. That processor depend upon the lab condition. You can use any processor, maybe small processor, maybe higher processor. Maybe you can do programming, maybe you can do based on the simulation that we can make. See the setup size, very small size, na? Then see the cost also. The inductor cost is fixed. All the converter this inductor you can put. Capacitor also, capacitor based on design only. This small capacitor only. Then other the component you can see. Maybe that resistance, maybe small inductor, those small capacitor, those we need to change. So in this case, this area is maybe somewhat you can say less costly and easily we can handle low power level. So you can see simulation and hardware. You can see how we have designed simulation value and hardware value. Here you can see. Now again we have redesigned the system. We have redesigned this complete that simulation. Previously we have designed for other power level, but for test of hardware we have designed for 3 watt. Input is 3 watt. Input voltage 12 volt. Input current 0.25 ampere. Output how much? 12 volt to 45 volt we have boosted. Now you can see here point 12 volt to 45 volt. Output current you can see 0.0425. Output resistance you can see 1065. Frequency 20 kilohertz. Duty cycle is 52. Switch rating you can see VC1, VS1, IS1, VD1, VD2, VD3, VD6, VD3 and 5. And then you can see VD4. All the voltage we can observe in simulation also. After designing the simulation, this 3 watt, na, for same parameter we have used for hardware setup. So in hardware you can see we have got a 2.88 volt, 2.88 watt you can see. Input how much volt? 12 volt we have given from that solar panel. Or maybe if you don't have a solar panel, you can give from DC power supply also, not power. You don't use solar. Here we want to prove the converter first. Second case, maybe you can use here input 2.24 ampere we can set by power supply also. Then 45 volt we need to boost. If we are going to use power supply, na, you can use maybe 6 volt also. 6 volt to 20 volt. Easily we can boost. Then you can see the output that resistance you can see we have the same value 20 kilohertz. Here we have got at 28% duty cycle. Then see that MOSFET, what MOSFET we have used. Then you can see the diode number you can see. Then inductor current IL1, VC1, V0, VC01, VC02. Those you can see. Inductor refill you can see. L1, L2 you can see 2 millihenry and 4 millihenry you can see. Output capacitor you can see. We have there for 1% refill only. So C1, C01, C02 you can see. Clear now? It means first we can design simulation. Simulation means result based on the whatever hardware you want to develop. For that one rating only, not more than that. Okay. So then after observing all those phenomena, same thing you can observe in hardware also. Means running the hardware not so typical, very simple only here. Here power level also very small. We can handle. We can put a hand there. Now you can see input voltage, output voltage, V in, V0. This is our system response. This is our requirement. We want input 8 volt we have given. Input current 0.17. Output is how much? 29 volt. Output current is 0.26 ampere. First we have taken here for 8 volt. 8 volt DC input. Then we can see all the VL1, VD1, VD3, VC1 plus. Depend upon your circuit how you are going to measure all those components. All the voltage you can measure. Gate pass you can take, VIN you can take, VS, IS you can take. VC01, VC02, VD5, ID5 you can see. You simply want to connect the DSO, you can find out all the waveforms. Nothing new. Okay. Simple, not very simple theory there. Nothing new, nothing we need to. Just we want to think how we can develop the. Just you can read theory, then you can develop new converter here. Means only 3 parameters we want to change: inductor, capacitor, and diode. How we are going to play, that is point. After that, you can see now we have 12 volt. Slowly we have increased the voltage. Immediately we have not given 12 volt. Then 12 volt to 45 volt. Second reading you can see V in, V naught, V in, V I naught. Then all the VL1, VD1, VD3, VC1, VD2, V in, VGS, gate to source voltage. Then you can see VS, then IS. Very simple thing. And VC01, VC02, VD5, ID5. Just only we have taken these curve means across all the component. Our first requirement is we want to boost input voltage to 45 volt with less ripple only. Here ripple also you can observe. Next is now you can see we have put dynamics also. Now immediately we want to first we have taken 8 volt, then we have taken 12 volt here. After that immediately we are going to change 8 volt to 12 volt. Now see the delay. 8 volt to 12 volt. How much microsecond that you can count. Here this is the result at 100 microsecond maybe. That one we are going to see 100 microsecond. So maybe you can see per division. You can see the change. Immediately also we can change to 8 to 12. Then based on that one you can see all the parameters. VL1, VD, VD3, VC1, VD3, VC01, VC02, VD5, ID5, all whatever component we have seen, the dynamic condition also we have observed. Okay. Now second converter means single switch ultra high gain DCC converter. So see here again we have changed the topology. Whatever circuit we have developed now, same circuit we have implemented in this breadboard. You can see. After getting there, that is a dismantle only, nothing new. Here we have some component, some party there, then here dismantle here and there. You see here the DSO, this is that inverter. You can see 6 IGBT are there, then that isolation card are there, gate points are there. Then that we have microcontroller we have used. In this case, simulation we have done at 2.76 watt. Hardware we have developed 2.88. Then you can see 12 volt to 44.43. 12 volt to 44.3 point this one. Then all this value you can see 28% duty cycle. There also we have put 28% duty cycle. 20 kilohertz. There also we have put 20 kilohertz. See the input current, output current, power. You can see the voltage. All the diode have same voltage 15.5 only. For previous cases 11. Some diode have 34 and 10 also. But in this case, all the diode have same voltage only 15.7. Continue. VS1 16.22 V, IS1 0.5. Then you can see this side also all the diode have 15 volt only. IL1, VC1, VC2, VC3, VC01, VC02 and voltage we have measured. So same value also you are going to have the hardware side. You can see almost nearby only 15.4, 15, 14.5, we have to 14.5 only, 28.5, in case of 29, 14.5, 14.5, 30 and 29. See the value of inductor. Simulation case we have used L1 2.6, the hardware 2 millihenry. See the value of capacitor ripple C1, C2, C3, C01, C02, 60, 120, 120, 60 and 120. So 47, 100, 100, 47 and 100. Okay. Again, we can see the result. Again, we have find out this result 8 to 12 volt. Only dynamics we have put here. So this is the gate to source, input voltage, input current, input voltage, input. Again, next case you can see input voltage, VS, VC1, V02. Output voltage, output current. Then dynamically we have changed 8 to 12 volt. See the all the waveforms. Again, in this area, what is the new thing here? What is the new point we can implement? That is based on the, again, when in literature many converter are there. Maybe that you can study. Then you can modify those some converter. One thing is there. Second thing, maybe after modification, again you can find the analysis. There means hardware analysis or maybe software hardware analysis based on that mathematical analysis you can say. Then also we can design their MPPT, different MPPT. We can use that solar converter, whatever solar system are there in that. We have to find out message MPPT. The message for and a duty cycle you can use some optimization. I will say we can use to find out proper value of duty cycle. We can run the system closed loop, open loop, both we can run. And again you can see to design implement the high gain DC converter with PV and battery based system. So first case maybe you can store energy in battery and then battery you can use. Maybe in daytime battery and solar both you can use. That possibility also there. Then after that you can convert in AC grid also. But solar supply there, then after conversion of DC value, then again you have inverter. Then after inverter again we are going to supply this one to AC grid. Okay. So next point is, okay, here just only we have whatever we have done that conclusion we have written this point. Based on MATLAB, we can do both open loop, closed loop, we can design then require voltage you can see. Any question here?
Participants,
This is a new thing.
Participants, you can put your question in chat box. I will ask on behalf of participants.
This is some new point that being new converter, some converter we can also design. This is the way maybe we can write the project also in India, maybe any small organization also we can write 50,000, 40,000, maybe 1 lakh. That project also easily we can get in this area. And 1 lakh or 50,000, maybe you are going to get, you are able 3-4 converters at least. Processor converter, then inverter, then also we need the battery, then we need solar system, then we need 2-3 processor you can see, then some switches we need, some PCB we need, some capacitor, inductor those we need. Usually mean below 40,000 or 50,000 usually all the company we will get. So maybe easily we can get 1 lakh or 50,000 maybe thereby those small cost project you can see. Based on that one we can do some work.
So I think so, sir, your slides are remaining or it's over?
Slide over.
Okay, fine. We will take few questions from the participants. Participants, please, if you have any query, you can put your question in the chat box.
One more thing.
Please continue, sir. Yeah.
So which book we have to follow? So first maybe you can start reading from Nen Mohan, Powerized by Nen Mohan, first book. Second book maybe you can use that RW erection you can use. RW erection, fundamental of power electronics and some disease covered some. Writer is RW erection, Springer publication. Second book. Third book maybe you can use that Aisa Batase, maybe that is Springer publication only. Or maybe other book, very publication you can see I placement. So 4-5 book you can download, maybe you can collect. Based on that you can develop this system. The paper also we need, paper also you can download some papers.
Even our books can be, that means referred for the understanding of these things. Me and Arya sir and Ahmed Aldura, one professor from
that is based on the distributed power generation.
Yeah, that is written based on distributed power generation, modeling and control. And that book is very much useful for basic understanding. Many authors have contributed in the contents of that book. 3-4 books are available from our side also in the market. You all are encouraged to download, or you can, that means refer to your libraries for better understanding of the readers and students. Now there is one question in the chat box. Mr. Sombir Kundu is asking, what type of load is taken in this waveform, linear or non-linear? So I hope so.
Linear load only.
Linear loads are taken. Dr. Sombir, you may have got the idea
Load we have taken.
just by looking the waveform. Yes, linear load. Yes.
Only resistance only we have taken. After that, after setting that DC bus, that voltage we have charging the battery.
Yeah. With these notes, I would like to invite Professor Divesh Parmar to sum up the session just by giving some concluding remarks about the session of the Arya sir. Divesh Parmar.
Yes, sir.
Yeah.
Namaste, Respected Professor Dr. Sabaraj Arya sir.
Namaskar.
On behalf of FDP team, our institution and all the participants, I would like to extend our heartfelt thanks for the enlightening lecture you delivered on design and control of high gain DC-DC converter and its interface with the solar system. Your detailed discussion of various topologies supported by simulation and experimental results provided invaluable insight that will undoubtedly help participants to accelerate their research in this field. You explained the complex topic of system design with remarkable clarity and simplicity. Your ability to break down, integrate concept, and deliver practical and actionable insights, both in this session, both engaging and inspiring. The way you skillfully addressed the participant question and fostered meaningful discussion significantly enriched the learning experience. We sincerely appreciate the effort you put into delivering this lecture at night, sir. Thank you so much once again, sir, for this wonderful lecture.
One more thing is there, means this is the one of the area. Second area also we can work in there of machine control. Machine maybe whatever machine induction, synchronous, PLDC, IPM, or maybe reluctance, maybe PLSM. All those areas also we can work with small machine, maybe 1 HP, 2 HP machine. With this is one side. Second side, till now whatever induction motor we have, that is the NAMA induction motor. Also we can use special type of induction motor useful in case of that traction system, maybe transportation, maybe 50 volt, maybe 24 volt, or maybe 96 volt per.
There may be some internet issue from Arya sir side.
Yes, sir. The voice is not coming
clearly.
Voice
is breaking.
Yes, sir.
But anyway, almost we have completed the session. And Arya sir, your voice is breaking actually. Hello? Some internet connectivity issue. Okay, sir. Now we will share your slides with the participants. And this lecture is also recorded on YouTube. Participants can refer lecture from there also. And thank you very much, sir, for joining us and for your wonderful delivery. Participants may have got a lot of things, topology and configurations, how to control the switches, and all these things are very much important for research. So thank you very much, sir. Thanks for joining us. It's our pleasure moment with you for 1.5 hours. It's very nice session, sir. Thank you very much, sir.
Thank you, sir. Thank you so much.
Now, participants, once again, I am requesting to all the participants, today's attendance was not so much encouraging. Almost many participants are seems absent today's in both sessions of today. Only 88, 89 participants have joined instead of 118 registered. So it is not advisable to bunk the lectures, that means sessions, and very easily you can join from anywhere. Either you are traveling or at home or at office. You can join from anywhere, and you can take the advantage from so many eminent personalities who are coming here and delivering the lectures. It is always encouraging point from my side. You don't bunk the sessions, otherwise attendance criteria also will come into picture. As per AICT rule, as already explained, 80% attendance is required for granting the certificate. So please be there for more than 80%, otherwise nobody can do anything. Attendance is downloaded directly from the that means MS team. Everything is on record. Nobody can say I was there, I was not there. Nothing will work. If you are here in the session, your attendance is counted. Not here in the session, attendance will be not counted. So it's very simple concept and fundamental. That's why my continuous and that means repeated request, you always join the session on time, take the advantage from all the sessions. Eminent personalities are coming here to deliver the sessions. Many new things you may be looking, you may be searching, and that may be useful for your further research. Some of you may be doing PhD, some have already completed PhD, but exercises and learnings never ends. You can continue to learn from these sessions. That is the motive of our FDP. Many things related to microgrid control operation and modeling is discussed in these 5 sessions. So please, my request again and again is to join the sessions on time. And tomorrow the sessions are based on control and modeling of microgrid operations. Different control techniques may be discussed. Some different topology you may have, you may see. And Professor Dr. Sukumar Misra, he is the director of IIT Dhanbad. Erstwhile it was known as ISM Dhanbad. So he is going to join tomorrow at 7:30, and Professor Deepankar Dev will join at 6 p.m. tomorrow for the first session. Second session will be taken by Dr. Sukumar Misra. Both are that means well-known personalities in their area, working area. So you can take the advantage of these sessions, future sessions, and you can learn something new, right? So this is all about today's session, and now we will wind up the sessions, and you can leave now. Thank you very much, Arya sir, for joining, and thank you very much all the team members for your that means for your cooperation, and thank you very much to all the participants who are continuously interacting, participating, and giving us motivation. Thank you very much, dear friends. I hope so. With all these words, good night to all of you, and we will meet once again tomorrow at 5:55. Now, till then, we can leave. Thank you very much, dear friends. Good night to all of you. Bye bye. Now we can leave. Hello, PK sir.
Yes, yes. Good night.
Good night. Good night. Devesh, good night.
Good night, sir. Good
Nitin
night.
sir.
Good night.
Nitin
Yes.
sir, good night. And yeah, hi.